In our last unit, we looked at the solar system and the universe and galaxies and the things that our universe are made up of. In this unit, we want to take a little bit of time to try to figure out how our solar system actually formed. And what we use to explain how our solar system formed is this thing called nebular theory. A nebula is a cloud of dust and gas. And in theory, remember, is an explanation of why things are. So laws state things are. Theories explain why we see the observations we do. Okay? So nebular theory is summarized in this picture. We start with this thing. This is a nebula, and this is a giant cloud of dust and gas floating around in space. Okay? Now, gravity acts on all particles with mass, and it pulls these particles with mass together. So the center of this thing is going to get denser and denser and denser. And as it contracts, this disk starts to spin faster. It's just like if you've ever twisted the chains up on a swing and then let it spin you around. If you kick your legs out, you slow down. If you pull your legs in, you spin faster. Well, as this thing contracts, it spins faster and faster and faster. And that causes this cloud to flatten out into a disk. And then gravity continues to pull this thing in, and that causes these particles to collide with each other. And when things collide, they get hot, and gravity continues to pull things together, so it gets warmer and warmer and warmer and warmer. Okay, so years and years go by. Center is getting so hot it's starting to glow, and these outer pieces of this thing are also starting to come together. So the chunks in this layer are starting to pull in things towards it. So we get these rings around it of denser parts of matter. As they get denser, the gravity gets stronger, and the planets are going to start forming in these rings. Okay? And then between these two stages, we go from this glowing ball of gas and dust with lots of gas scattered around to not so much gas scattered around anymore. And that's because the star actually began. It started doing nuclear fusion. And when it does that, it creates an immense amount of heat and radiation that blows away from the star, pushing the lighter elements out away from itself. And then a few 100 million more years go by, and we get the solar system. We have well-defined planets and well-defined orbits. So let's take a little bit closer look at that. First, we have to understand what a nebula is and what gravity is, how it works. A nebula is just a large cloud of dust and gas. It's found in space. There's all kinds of them. There's some pretty cool ones. There's some pretty neat pictures of this taken by like the Hubble Space Telescope. You can look for pictures on the internet. They're pretty. Nebular theory explains that the solar system and stars form because gravity pulls a cloud of dust together, pulls the nebula together. Gravity, remember, is a force of attraction, and it acts between any two objects with mass, but it's not a constant force. Gravity is a force that depends on mass and distance. So Newton actually was able to describe how gravity works, and it's dependent on mass and it's dependent on distance. If you increase the mass of an object, the gravitational force will also increase. If you decrease the mass, the gravitational force will decrease. And you guys have probably heard this before. You have a weight here on Earth because Earth's gravity is pulling you towards it. If you go to the moon, you're going to weigh less because the moon has less mass, right? The moon's little, the Earth is big. You stand on the moon, it has less gravity pulling down on you, so you weigh less. You stand on Earth, there's more gravity, you weigh more. If you could go stand on Jupiter, Jupiter's big, okay, you couldn't really stand on Jupiter because it would crush you because gravity's too strong. Also, it's gas. The other thing that gravity depends on is the distance between the objects. So the reason the planets are all in orbit around the sun's giant, and the planets are fairly small compared to them. Okay, we got our planets out here. There's actually a gravitational force of attraction between the sun and every single one of these planets. But the gravitational force of attraction is stronger over shorter distances and weaker over longer distances. So the further you are away from Earth, the less it's able to pull on you. The closer you are to Earth, the more it's able to pull on you. Now, how does this lead to a star? How does gravity lead to a star? Well, remember, a star is a luminous body, and it's undergoing nuclear fusion. So in order for nuclear fusion to happen, it needs to get really, really, really hot. So gravity's contracting this nebula, pulling all the particles together, and that makes the cloud get smaller, and it spins faster, it flattens out, and the core continues to contract. gets very close to each other. The particles start colliding, running into each other. That gets the core hot, and that forms a protostar. A protostar is not truly a star yet. It is hot enough to be glowing, but it is not hot enough to be carrying out nuclear fusion yet. Okay, so gravity is still able to contract this even more, gets it even hotter, and once it gets hot enough, it starts undergoing nuclear fusion, and that's when we actually have a star. So when the core of this nebula starts doing nuclear fusion, we get a star. Now that's cool because we have two forces going on. In the middle of the star is nuclear fusion, which is making everything really, really incredibly hot, pushing out. But gravity is in the core trying to pull everything in. So a star is giant. It's got to be huge to have enough mass, to have enough gravity to pull things in close enough to get it hot enough to make nuclear fusion happen. And then the nuclear fusion is actually trying to push against gravity, expanding everything. So there's this constant struggle in this star of gravity trying to crush it to death and the heat produced by fusion trying to expand it and push things away. So nuclear fusion starts and our star is born. And then what that causes on the nebula scale is all this cloud that was out here, well, this giant amount of radiation that comes pouring out of this star is going to push away all the lighter elements that it can. So the gases that were floating fairly close to the core are going to get blown by solar wind away from it. And so that explains why our inner planets are the rocky terrestrial planets and our outer planets are the gaseous, bigger planets. So the immense gravity of the star keeps the nebula, that's that cloud orbiting around it, even though it got really hot, gravity's still acting on those pieces. The heavy elements are closer to the star and they start to pull together. The lighter elements were blown away. Now there's not very many heavy elements because they're not very common. Most of the elements, or most atoms in the universe, are hydrogen or helium. So there's very little matter near the star. Most of it's either sucked in this part of the star or blown away and is out in the outer edges of the solar system. So there's a little bit of heavy elements left, and gravity starts to pull those together into clumps, and they start getting bigger. So we're going to get small rocky planets on the inside, the lighter elements are blown to the outside, and we get the gas giants out there. So gravity, again, is going to pull those particles together into planets. That is a process called accretion, when small chunks come together to make the big planets. And this all started happening around 4.6 billion years ago. So our solar system dates to about 4.6 billion years. Now, there is some other stuff that isn't really a planet or a star. It's just sort of orbiting. The asteroid belt is between Mars and Jupiter, and it's not a planet. It's a whole bunch of debris. And the thought on that is, right, we've got Mercury close to the sun, Venus next, Earth next, Mars next, asteroid belt with a bunch of junk, and then Jupiter. And Jupiter's giant. Jupiter's huge. It's got a bunch of gravity. Okay, so gravity of Jupiter was actually pulling on these things. The gravity of the sun is pulling on these things. The gravity of themselves is pulling on these things. And all that gravity is messing with it. And it prevents all of these things from actually coming together to form a single planet. Since these planets were farther from Jupiter, they didn't have to deal with that issue, and they were able to form together into planets. So the asteroid belt is the remnants of the nebula that didn't get accreted into a planet. And those are heavier elements. Those are carbon and silicas and metals. So the asteroids out here, those are fairly heavy elements. Okay? And then the Kuiper belt, which is out on the outer edge of the solar system, sort of a similar thing going on. It's leftover debris from when the solar system formed. None of it really came together. There are some fairly big chunks out there, including Pluto and a couple other dwarf planet-sized things out there. But these ones are not the heavy metals. These ones are lighter compounds. They're frozen because it's way cold out there, far away from the sun. So they are solid, but it is things like methane and ammonia. So there would be gases here on Earth. Okay? So the nebula, this cloud of gas and dust, and gravity work together to make a star in the middle and the planets around it.